Early memories. Of course, I entered this world like everyone with eyes closed. My very first memory of sight was the fluorescent light tubes over my head in a doctor's office. They didn't do anything, but boy, they were brighter than everything else. What was that about? I remember thinking in a wordless way. That may have been the awakening of my lifelong fascination with light. At the age of 5, I saw my first total lunar eclipse. I expected the moon to disappear, but it didn't. Instead, it darkened. Could we have that slide, Jeremy? Oh, by the way, the monitor up here is much easier to see than the one in the back. Some of the one in the back doesn't have great contrast for some of these. Instead, it darkened and turned red. My father had a Socratic discourse with me. He said, "When the sun sets over the horizon, what color is the sky?" I said, "Red." And he said, "And before it rises, red?" He says, "Now imagine you're on the moon during an eclipse. Where would you find the sun?" "Well, it's behind the earth." "So it's just under the horizon all the way around." "Yeah, I guess so." "So the only light you'd be seeing is from sunrises and sunsets all around the world." Oh. That was one of my earliest encounters with inductive reasoning and one of my first with geometric and physical optics and astronomy. And when I turned 8, I made a telescope from an Edmund surplus catalog kit, grinding and polishing my first mirror. That was my entry into optical fabrication, which became my career. Edmund Optics has since morphed into one of the world's largest and best recognized precision optics suppliers, and I know perhaps a dozen people working there. Next slide, Jeremy. Now, this is viewed from an airplane on my first airplane trip. It's called a glory. If you look very closely, you can see a second rainbow around the first. And I noticed that it was centered directly on the seat that I was sitting at. How did they know? And my first partial eclipse of the sun graced me with crescent-shaped shadows dancing under the trees. But I couldn't get anybody else to look down. Later, my first total solar eclipse a few years ago left me absolutely breathless, awestruck, trembling. Lori can vouch for that. I was just, And playing in the sprinklers as a child, I saw rainbows against the grass and discovered that I could never get to their ends. Now, at the ripe age of 17, Jeremy, the next slide, please. I saw the great comet, Akaya Seki, almost as bright as the moon. It was a fabulous sight. So we moved forward to my studies. College was during the late 60s, amidst women's lib, Vietnam, civil rights, and flower power. That last influenced me to this day, as should be obvious. I was one of the first flower children. We wore daring colors, flowers, and ribbons, and we spoke of the cosmic and of Eastern and indigenous religions. I was exposed to Alan Watts and then Yogananda, who wrote of a different sort of God, one who was indwelling, patient, loving, one whom we could experience by tuning our minds to the all-pervasive consciousness that was the ground of being. And in his autobiography, the chapter, The Science of Miracles, summarized Vedantist beliefs about the universe, that it was formed by precipitation of the original great white light into all physical manifestations through the eternal dance of Shiva, the god of creation and destruction. The world we see and imagine is Maya, illusion. Just around that same time, my physics classes had advanced beyond levers, springs, billiard balls, the things that we can see, to an initiation into the deep mysteries of the learned, pulling back the curtain of what's really going on. Next slide, Jeremy. Now, this is a beautiful symmetry with many copies of the Star of David. It's one cut through all those symmetries of the mysterious particles, what the heck they are, a zoo of particles made of who knows what, finding their places in a beautiful multi-dimensional symmetry. And this is just one projection of that symmetry. Next slide, Jeremy. This next one is from the Theory of Everything org's book, The Star of David. Blog, I mean. A zoo of waves that don't need any ocean to travel. And particles, but made of what? Suspended in a vacuum? Matter being both particle and waves. Matter, which according to Einstein was concentrated knots of energy, and energy, that capacity to make matter do things. But I just said energy and matter were the same. I learned that in this symmetry of particles, if a particle and an antiparticle meet, they annihilate each other and create a pair of photons. That's light. Light, by the way, doesn't have an antiparticle. It's the only one. Photons are the only ones that don't have antiparticles. So I asked my professor, what if we had enough light in one place? Could we create matter? He said, yes, theoretically, but there's no way we have light of creating light so powerful. And that's when it struck me, Yogananda was right. The Big Bang was just such an instant. At first, there was no particles at all. They couldn't hold together, just an incredible flash into a space not yet the size of a pinhead. And as things cooled over a few trillionths of a second, and then a few 100,000 years, all the light, all the particles formed, and all the light was absorbed and re-emitted by this dense plasma. Couldn't travel the tiniest distance without something wanting to check its papers. After that time, things had cooled enough that space became transparent. There was light, and God said, good. Whew, I'm glad that I don't have to do that again. Such hot work, and in the dark, too. Even today, virtual particle pairs pop in and out of existence, unseen and everywhere, unbidden. Truly, everything we see with light was precipitated from the first light and sustained in a dance of creation and annihilation. That is a poetic, if not incorrect, view of the physics of the universe. Next slide, Jeremy, please. Now, one day in a college lab, I looked into a mercury lamp through a Fabry-Perot etalon. Don't worry about it. And I was smitten. Look at that. I fell in love with light and all of its mysteries, but this picture is not nearly as stunning as that sight. I did what I could. I picked from my collection an old Fabry-Perot etalon, stuck it in front of my phone, and aimed it at my monitor. But next slide, Jeremy. Here is a higher resolution, sort of what I saw. That mix of lights repeating again and again. Well, okay, so my career, since my physics education then centered on optical physics, my entire career has been involved with precision optics. The things that create and manipulate and detect light. You may know some of them: mirrors, prisms, lenses, windows. There are many more with obscure names. After graduation, I got a wonderful opportunity to work on big telescopes. Jeremy, next. In Tucson for my first real job. And I learned from master opticians. My first mirror was over 8 feet in diameter and weighing 4 tons, and it's still working in a Chilean observatory. This is Lori and me in 2014, standing a story above and some distance away from the LSST mirror that's now in the Nancy Grace Roman telescope. And that lab is now making the world's largest telescope mirrors all the way from casting to final finish. For those who don't speak metric, that one is about 27 feet across. And that was just before it got its brilliant mirror coating. Jeremy, the next. There it is, just coming out of the coater. Last week, it saw its first light in Chile at the Nancy Grace Roman Observatory. It is in many ways far more capable than Webb. It has the world's largest and highest resolution camera, each image covering an area of sky 3 million times the size of a single Webb image. Webb looks for the details way out in the distance. Nancy Grace Roman does a survey. And it has a resolution equivalent to 400 HD TVs. So you can imagine filling this entire floor with HD TVs and having to come up and look in a magnifying glass at any area to see the detail. And it takes an image every 15 seconds, surveying the entire sky in a few nights. These telescope projects take about 30 years each, but I didn't have 30 years. In 1972, a cut in funding took me out of Tucson and away from telescopes, and oh, how I missed them. But then I learned the ways of lasers. And after several jobs and several capacities in several states, my career brought me to Florida, where I met Lori, the steady and beautiful light of my life. Aw. But light is so central. Every piece of evidence we have of places that exist beyond the earth, and everything we've learned about them, has come to us through light. Well, except for comet dust and a few moon rocks, but we needed light to know they exist and how to get there. And as a metaphor, it has a central place in religion and philosophies. While my career was about methods to make things related to light, and I've contributed to that field, my fascination with light itself is the thing. Let's think of the word itself as a metaphor. It's woven inextricably into our language. The Buddhists and the Hindus seek enlightenment. We desire to be around people who are sunny, bright, colorful, luminous, sparkling, and scintillating, not those who are blind to life's delights. We look up to those who are shining examples, who envision a better world. We desire to lighten our burdens and make light of them. Paradoxically, even the name of the Prince of Darkness is Lucifer. We elucidate or illuminate or shine a light on a subject by a brilliant explanation. Our own publishing house is Beacon Press, and as Margie mentioned, we strive to be a beacon. And we light our chalice weekly. Press conferences are judged on their optics. See what I mean? I hope all these reflections are brightening your morning. Next slide, Jeremy. But what is light? The nature of light is still one of the deepest unknowns, even as we depend on it to navigate through our days, to deliver our emails through fiber, to show us cat videos, and to grow our food. Well, light, it's not heavy. It has no mass at all. It has no antiparticle. We know what it isn't, but what is it? We haven't the faintest idea. Although we have lots of equations to describe how it behaves, its true nature is still being discussed in conferences. Two of this book's authors have been my friends for several decades. Their conferences continue annually without resolution. Now, in the last couple of centuries, Young's double-slit experiment, Einstein's Nobel Prize for the photoelectric effect, and Michelson and Morley's interferometer give us some inkling into its weirdness. Next slide, please, Jeremy. In 1801, Young shone light through a slit onto a screen and saw, as any reasonable person would expect, a slit-shaped image. A wave or a particle would do that. But when he sent the light through two parallel slits, he didn't see two slit patterns, but rather a series of bright bars, as you see up there. He deduced, and for a century everyone agreed, that the light was a continuous wave. It had to be. Part of the wave went through each slit and then brightened the screen where those parts found themselves in phase. Then Einstein messed it up after a century. His experiment was analogous to throwing BBs onto a pile of marbles. Above a certain momentum, even one BB would dislodge a marble. The more BBs we threw, the more marbles came off. But below a critical value, it doesn't matter how many BBs you throw, marbles were undisturbed. Obviously, the stream of BBs consists of separate particles. He did this with light. He did this with electrons. A stream of light behaved the same. So light must be a stream of particles delivering a kick. Wait, what? Well, let's check that. Let's just go through one slit at a time, and we'll cut the brightness down so that photon detectors count separate hits. Click, 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 click. Then the other slit, click, 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 click. They still hit the screen hard enough to knock off electrons. In either position, they must be particles. Next slide, Jeremy. Ha ha. Now we remove the detectors so that we don't know which slit it went through. A pattern of dots. Yeah, they look like particles, but they're arranged in an interference pattern. So what is going on? Is it a particle that goes through both slits simultaneously? Is it a wave that packs the punch of a particle? Does it know whether we're watching? Nothing makes sense. And Richard Feynman said, nobody knows, and it's best if you try not to think about it. Nobel laureate Roy Glauber slyly defined the photon as what a photon detector detects. And what about the speed of light? We know we're traveling around the Earth, which is also traveling much faster around the Sun, which is moving even faster across the Milky Way. So if light is traveling through different amounts of space in different paths to arrive at the same screen, it must take different times. Williamson and Morley devised a very sensitive experiment to check that. Nope. Not at any time, in any day, or in any season, in any amount. It's been repeated for the last century. Not a bit. And yet Einstein claimed that when we travel faster, time takes longer. And it does, because our GPS wouldn't work without those exact corrections. So what's up with that? This rabbit hole goes all the way down, so let's escape while we have a chance. Next slide, please. Now that is our visible spectrum, and the tilted lines point towards the area in the electromagnetic spectrum that has light. The long wavelengths at one end look red to us, and the short ones at the other end look violet. Beyond those are infrared and ultraviolet, good names, which we can't see. Beyond those are X-rays and radio waves, all the same stuff, out to gamma rays and cosmic rays. Out of a range of more than 10 billion to 1 in wavelengths, we see a range only 2 to 1 right there in the middle, in a straight line, just like one octave on a piano that's miles wide. But how do we see? These photons, whatever they are, come to us either directly from a source, like the sun, like these lamps, like our candle, a TV screen, or indirectly as they bounce off of objects like the floor, my face, a book. Our eyes sort them by the angle that they come into our eyes, where they land on retinal cells, and the rods don't discriminate color at all, but they're very sensitive to low light. That's how we see in the dark at night. And that's why we don't see green grass and red flowers at night. And when we look at the night sky, we don't see the gorgeous palettes that telescopes see. Next slide, Jeremy. But the cones come in 3 varieties, each sensitive to overlapping bands of colors which peak around red, green, and blue, but they overlap a lot. Our retina's cones absorb the light according to their 3 types, and they cause a chemical reaction in our eyes that goes all the way to the back of our brains. Why? I don't know. And how such electrical charges turn into conscious sensation is the other deep mystery. Consciousness. Because something cameras don't have. Let's leave that rabbit hole to another time. Anyway, the intensity of those signals from the long, medium, and short bands, the 3 cone types, are compared in the brain. The long and medium have a broad overlap, as you can see there. The green and the red overlap so much. What do you think is in the middle between green and red? Look down. It's yellow. So when we're exposed to a pure wavelength somewhere between pure red and pure green, our brains get input from both. And depending on their relative strengths, we'll see yellow, chartreuse, or orange. And here's one place where we get tricked. Yellow from a prism is a pure wavelength, and both the long and the medium cones respond to it. And when we're exposed to pure yellow, Our brains have no yellow receptor. They fire off red and green and tell us it's pure yellow. But when our monitors send us only pure red and pure green, we see only yellow. Try it sometime. Get a magnifying glass, find a screenshot of a ripe lemon. There's no yellow in it. By the way, a real lemon looks pure yellow to us, but it's reflecting a great deal of green and red. We can discriminate fairly accurately as much as 2 million colors with just these 3 receptors. Another miracle. What about violet, though? That's a pure color, and we don't have a violet receptor. But if you look very closely at the left end of that, the red picks up a little bit just as the green drops to 0. So we see that as red and blue, and we think violet or maybe purple. And I like to think that that red tail is folding over in our brains to connect with red on the right side, giving us that sense of a color wheel rather than a musical scale. But now we get into trouble. There is no magenta anywhere on the spectrum. There's no maroon, fuchsia, or purple. Instead, our brains wrap that keyboard into a circle, tying the violet end to the red end, and we invent the color magenta. We're also, by the way, tricked to call a dark yellow by the word brown. That's mostly linguistic and cultural. We were taught there were 7 colors. How did indigo get on that list? And what about azure, alizarin, aubergine, chartreuse, crimson, celadon, carnadine, cerise, viridian, puce, lavender, maroon, periwinkle, ochre, beige, ecru, mauve? We have millions. And except for lasers, prisms, and rainbows, any bit of light coming into our eyes is a smear of ranges of wavelengths. That's why artists mix pigments. Next slide, Jeremy. Thank you. Now, I created this little snake on my screen by starting with defining the color red only, no green, no blue. And then on the right, it's green only, no red, no blue, and so on. So from the green to the red, I have different mixtures. From the green to the blue, I'm mixing those two. And from the blue to the red, I'm mixing those two without any green in the middle. This snake can be turned into a wheel, but look at something interesting. Right down the middle is yellow, cyan, and magenta. Ooh. That's magenta, huh? Yeah. All right, so all the colors we see are our brain's interpretation of just those 3 signals. Painting works by absorbing or subtracting. Our monitors add pixels of different color. Paint pigments subtract colors. And that's why we have an RGB monitor, but if you look at your printer ink, it's CMYK for cyan, magenta, yellow, and black. So, what next? Next slide, please. There's our color circles. RGB on the left, where we add red and green, and we get yellow. And opposite yellow on the bottom is blue. Look on the other side. Now we've got blue on the top in the middle and yellow on the bottom. Ooh, try that all the way around for any of them. They're all symmetrical. It looks like it's a real wheel to us, but it's not. It's just a mixture of different wavelengths. So very weird. So now you see, or how do we see, really, that it is a miracle that we make any sense out of this at all. Most painters choose pigments close to what they want, and they mix them with other pigments, which is subtractive. But then the pointillists discovered a new way to do it. They basically hit dots of contrasting colors next to each other like pixels, and that gave us a brightness that you don't see elsewhere in paintings. This is Georges Seurat, and the next slide, and I believe the last, is by Sagnac. So they added wavelengths, more like a TV screen. Anyway, in summary of all of this, surgery, astronomy, oceanography, computer chips, fiber optics, solar power, welding cars together, detecting clear air turbulence from airliners, food safety, crop health, earthquake early warnings, stresses in bridges and wings, lighting, night vision, weather satellites, paintings, sculptures, movies, reading QR codes. Truly, we can't go more than a few seconds today without depending on some sort of optical gear, creating, sorting, transporting, or measuring the light. And that's where I've spent my career. As we had promised in our call to worship, to nurture this light, let us reflect for one more moment. We know that light lives gently, for it has no mass, traveling invisibly until it meets the end of its journey. It loves mightily, warming our planet, nurturing plant growth, illuminating the cosmos, allowing us to navigate safely and see the glories of the universe, of art celebrating those glories, and of each other's faces. And we bow to its mysteries, for whatever it truly is has not yet been conceived after centuries of thought by the world's best minds. And yet, no one can doubt it exists. The future is bright, and hey, it's Sunday. Thank you.